Number 4 reads, one day we hope to tap the power of the nucleus for a clean alternate form of energy. The nucleus of the helium atom contains 2 protons that are separated by about 2.5 times 10 to the negative 15 meters. Find the magnitude of the electrostatic force that each proton exerts on the other. And then there's a hint. Remember that protons have the same elementary charge of an electron, which is 1.6 times 10 to the negative 19th coulombs, except it's positive for a proton, negative for an electron. See section 22.8, Coulomb's law of your textbook for help. And then remember that protons are able to stay together inside the nucleus because the electrostatic force is balanced out by a strong nuclear force. This is what happens in the sun right now. The reason why we can see light and we get heat is because the sun is a giant ball of hydrogen and helium gas. And there's an atomic reaction called fusion where the helium-hydrogen nuclei are squished together from the big gravitational field of the sun. When you do that, all the energy that's stored inside the nucleus from the protons trying to push apart and the nuclear force holding together, bam, it's like cracking an egg open, except instead of just getting like an egg yolk, you get lots of nuclear energy coming out. Okay? So nuclear power isn't bad. It's just, it's bad if you make bombs and kill people, right? But it's natural. That's why we're not dead, because we get sunlight and heat and all that. Okay? So one day, hopefully we can figure this out. You guys ever see the old Back to the Future movie with Michael J. Fox? And at the end of the movie, Doc Brown comes back from the future. Great Scott! And then he takes off in the converted DeLorean time machine. And I think it's pretty funny because they converted the nuclear power plant to Mr. Fusion. It looks like a blender. And he digs around in the garbage and he throws in like banana peels and an empty beer can or whatever, right? So anyhow, let's plug and chug. This is a 4-step problem, so we're going to make a little what first? We're going to make a little sketch to see what's going on, okay? So this is number 4 on our website. So here we have the nucleus of a helium atom. It's got 2 protons, okay? There's also 2 neutrons that don't do anything. We don't care about those, okay? And what do you know about protons? Do they like each other? They don't, right? They're trying to push apart, and there's some kind of force acting on them, which we'll figure out in a second, okay? So that's just a basic idea, not a big deal, okay? Step 2, list all of the what? Knowns and unknowns. For Coulomb's law, we have F, K, Q1, Q2, and then the distance squared, right? Will be the equation. So we just got to plug in the numbers, okay? The only number that they give us is a distance, 2.5 times 10 to the negative 15th meters, okay? Big number or really small? Yeah, negative 15th is super small, right? It's smaller than a trillionth of a meter. I don't even know what that is. Quintillionth? Whatever, right? It's so small it pretty much means nothing because on an atomic scale, it's smaller than light. It's invisible as far as we know, okay? That's okay. Q1 is a charge of the first thing and Q2 is a charge of the second thing, and they're both an elementary charge, which is the charge of an electron or proton, and that's just given as 1.6 times 10 to the negative 19th coulombs, okay? And that's just a basic fact that you probably want to put down on your note card, okay? In the early 1900s, Robert Millikan won the Nobel Prize. Yay! Okay, an American scientist at the University of Chicago, right here. Yay! He measured the charge of a single electron by doing a really brilliant experiment. He sprayed oil droplets into an electric field, and he put electrons on until it floated. And since he knew the weight of the drops, he could figure out the charge of a single electron. Crazy, right? Actually, rumor has it that he actually wasn't really nice. He made his graduate students do all the work, and he took all the credit. But that's life, okay? K is the electrical constant, which is 9. It rounds off to 9 times 10 to the 9th, okay? Newtons times meters squared over Coulomb squared. It's just a constant that makes the equation work, okay? You don't have to memorize that. You just have to know that value. Again, put that on a note card. And then the only thing left is to find the force. That's what we're really trying to figure out. What's this force in newtons? That's our unknown, okay? So this is really a straight plug and chug question using Coulomb's law. The hard part was just knowing how to use the equation, okay? So step 3, we write out our equation, Coulomb's law, F equals K, Q1, Q2 over the distance squared, where K is the electrical constant, Q is the charge on object 1, Q2 is the charge on object 2, and then D is the distance squared. So now we just plug in all our knowns and unknowns, okay, in step 4 into our equation. What do we put in for F? F is our unknown. K is our electrical constant, 9 times 10 to the ninth. We're going to leave off units until the very end, just to make it easier, okay? Then we have Q1 and Q2, which is 1.6 times 10 to the negative 19th. And since there's two protons, they have the same charge, I'm just going to square that because we're just multiplying the charge by itself twice over the distance squared, which was 2.5 times 10 to the negative 15th squared, okay? So the hardest part about this problem is probably just putting in our calculator. Holy cow, what a mess, right? So we'll get out our calculator. You get out yours, I'll get out mine. I got my little virtual calculator. Yay. Turn the sucker on, okay? And I noticed in my last class, some people were still entering the exponents wrong. You want to hit this EE button, okay? To give you luck. Actually, let me clear out my calculator here. There we go. Reset it really quick. There we go. Okay, so the first thing I'm going to do is I'm going to do 9 times 10 to the ninth. You want to hit the second EE button, okay? Oops, I whiffed. Second EE. There we go. And that means times 10 to the ninth, okay? Some people were doing this e to the x thing. That's like natural logarithm. Don't do that. That doesn't work, okay? So I have f equals k, 9 times 10 to the ninth, times q1 times q2, which is 1.6 second e negative 19th, and I'm doing it twice. I'm just going to square that as a little trick to make it easier to enter. Finally, I divide that by the distance squared, which is 2.5 times 10 to the negative 15th. Oh, I got to put that in parentheses, right? Order of operations. There we go. 2.5 second e negative 15th, and then that sucker gets squared, okay? So I got to have that in parentheses so that my order of operations works out. And when I do that, I get a force of like 36.864. We'll just round that off to 36.9, okay? And what's the units for force? Units for force is newtons, okay? So what's weird is, even though a proton has such a small charge and the distance is so small, we actually get a really big force. It doesn't seem like a lot of force because a newton is only about 1/5 of a pound, so that's only like whatever, 7 pounds of force or whatever. But this is on an atomic scale, right? So if you multiply by the trillions and trillions and trillions of helium atoms and nuclei in the sun undergoing thermonuclear fusion, you can see that then there's a lot of energy involved when you release it. It's like a spring. You unlatch a spring. Okay? So in a nutshell, that's number 4. We're just plugging and chugging using Coulomb's law.